одна будешь досиживать.
Когда совсем никого нет, как-то мысль о том, что смотрит, что кто-то меня смотрит там, она, конечно, греет, но все-таки как-то немножко не по себе. Когда нет совсем никого. Так.
Кстати, можно посмотреть, сколько там просмотров набирается.
Нет, там, в общем, смотрит вроде бы.
Но я ни разу не смотрел, мне вот стало интересно.
Пошел в эфире.
Посмотреть, сколько там просмотров.
Okay, so today our first goal will be to introduce the injective tensor product of locally convex spaces. Okay, so in contrast to the projective tensor product, which is defined by a universal property, the injective tensor product is given by an explicit construction. So we start with a pair of locally convex spaces, x and y. We take a continuous seminorm P on x and a continuous seminorm Q on y. We introduce the following notation. We denote the injective tensor seminorm on the tensor product or on the tensor product of x and y corresponding to P and Q by the following formula. So this is the injective tensor seminorm on the algebraic tensor product associated to P and Q. So in other words, we simply consider x and y as seminorm spaces with respect to the seminorms P and Q, and we form the respective injective tensor seminorm. Let's recall an explicit formula which defines this seminorm. So if little u is an element in the tensor product, then this seminorm of u is defined to be the following supremal f tensor G applied to u, where f runs over the closed unit ball of the dual of x. So here we forget about all other seminorms and remember only the seminorm P to form the dual space. This is seminorm space. And we let f run over the unit ball of the space. And similarly, G runs over the unit ball of the space dual to x cubed. So this is the definition of the injective tensor seminorm. Now we define the injective tensor product, the injective tensor product of x and y to be the algebraic tensor product equipped with the locally convex topology generated by all seminorms of this form. The algebraic tensor product together with the topology generated by all such seminorms, P tensor Q, where P runs over a family of all continuous seminorms on X, and Q runs over the family of all continuous seminorms on Y. And the complete injective tensor product is defined to be the completion of this space. The complete injective tensor product is the completion of the space, and it is denoted like this. we simply put a hat over the tensor product sign. Okay, so it's rather easy to observe. It's a simple exercise for you to show that we can actually replace here the families of all continuous seminorms on X and Y by arbitrarily defining directed families. So if P and Q are defining directed families of seminorms, on X and Y respectively, then we can replace the family of all continuous seminorms of X by P. And similarly, the family of all continuous seminorms on Y by Q. And we get the same topology. In particular, if X and Y are seminorm spaces, then we come back to our earlier definition of the tensor product of two seminorm spaces. So the respective topology is defined by the single seminorm, the projective tensor product, or the injective tensor seminorm corresponding to P and Q. Okay, let's now compare the injective tensor product with the projective tensor product. A little observation. Roughly, we will observe that the injective tensor topology is weaker than the projective tensor topology. More exactly, I mean the following. So let's draw the following picture. We have the projective tensor product here, and the injective tensor product of X and Y. Here we have the canonical map theta. For convenience, let's denote them by some subscripts, theta pi and theta epsilon. And here we have a map denoted by I, which is essentially the identity map from the set theoretic point of view. But remember that it acts between two different local convex spaces. So here we have the projective tensor topology, and here the injective tensor topology. And let's recall the following inequality. The injective tensor seminorm is less than or equal to the projective tensor seminorm. For the simple reason that the projective tensor seminorm is the largest possible, the greatest possible reasonable cross seminorm on the tensor product. And this one is the smallest one. So we have this inequality. And this inequality rather implies that I is continuous, because the topology here is defined by these, by seminorms of this form, and the topology on the projective tensor product is generated by seminorms of this form. So this implies that I is continuous. That is, in other words, epsilon is included in pi. So the topology on this space is weaker than the topology on this space. Moreover, the same, the continuity of I implies that theta epsilon is continuous. Theta epsilon is also continuous, simply because it's the composite of two continuous maps, this one and this one. Let's now look at the completions of these spaces. So we have the complete projective tensor product here, and the complete injective tensor product here. And here we have theta hat, pi, and theta hat epsilon. Now the universal property of completions gives us a map from here to here. I hat. So this map I uniquely extends to the completions. An important warning concerning this map is that in general, this map I hat is neither surjective nor injective. I itself is one-to-one, of course. I is an algebraic isomorphism. But I hat is not necessarily surjective, and moreover, it can have an untrivial current. In fact, examples where I hat is not surjective will be discussed at the end of today's lecture. On the other hand, examples where this map is not injective are much harder. They are related to the possible absence of the approximation property, and so we will not discuss such delicate things in our course. But cases in which it is not surjective will be given explicitly. Okay. Let's now recall that the projective tensor product is actually a functor of two variables. So it's natural to ask if the same result holds for the injective tensor product. And the answer is yes. We have the following proposition, which essentially means that the injective tensor product is a functor. If we have two continuous linear maps, phi I, between locally convex spaces, xi and yi, so yi is either 1 or 2, then there exists a unique continuous linear map, phi 1 tensor phi 2, between the injective tensor products such that it takes every elementary tensor x1 tensor x2 to the elementary tensor phi 1 of x1 tensor phi 2 of x2. Moreover, part 2, if our spaces are semi-normed spaces, if xi and yi are semi-normed spaces, then the norm of this operator, of the injective tensor product of phi 1 and phi 2, is equal to the product of the norms of phi 1 and phi 2. And the same is true for the complete injective tensor products. Similar results hold for the complete injective tensor product. To prove this result, it will be more convenient to start with part 2.
Сейчас, первый пункт это какое-то алгебраическое утверждение чисто, да?
Unique, yeah, sorry, it is algebraic in this form, but I forgot to say that it's continuous, of course. It is the fact that such a map exists and is unique is an algebraic fact, and I'm assuming you know this fact. The point here is to show that it is continuous. Mm-hmm. The point is to show that it is continuous. So we start with the second part. So we have the following picture. So again, as I just already said, we assume that a linear map with this property exists and is unique. So we have to prove that it is bounded and its norm is equal to the product of the norms of phi 1 and phi 2. So we have the following picture. This is our map, phi 1 tensor phi 2. And let's recall that we have a canonical isometry from the injective tensor product of x1 and x2 to the dual of the projective tensor product of their duals. Isometry. So this isometry was constructed at the previous lecture. And we can do the same construction for y1 and y2. So we have an isometry from the space to the dual of the projective tensor product of the duals. But we already have a map from here to here. Well, what is the map? Well, this is the dual of phi1 prime tensor phi2 prime. And it's very easy to show that the diagram commutes. A little exercise. Okay, now let's now calculate the norm of this map. We'll show that it is finite and that it is equal to this product. Y1 tensor phi2. This is the injective tensor product, and this is the projective tensor product. So since these two vertical arrows are isometries, we see that the norm of this arrow is less than or equal to the norm of this arrow. But, well, this is the dual. This is the dual of a linear operator between normed spaces, of semi-normed spaces. In any case, the norm of the dual is equal to the norm of the original map, phi1 prime tensor phi2 prime. And we already know from the previous lecture that for the projective tensor product, the norm of this map is equal to the product of the norms of phi1 prime and phi2 prime. And this is exactly what we need. So we have this inequality, and the opposite inequality is a simple exercise. To prove the opposite inequality, it's enough to look at elementary tensors, to apply our map to elementary tensors, and to reduce that, we have this inequality. So this completes the proof of part 2. Part 1 now can easily be deduced from part 2 as follows. So we want to show that this map is continuous. We take two continuous seminorms on y1 and y2 respectively. So take qi is a continuous seminorm on yi. I is 1 or 2, and define a seminorm pi on xi in the following simple way: qi composed with phi I. So clearly this is a continuous seminorm on xi. And if we equip xi with the seminorm, then phi I is a continuous map between the respective seminorm spaces. So let's recall that x with a superscript p is our short notation for x equipped with the seminorm p. So if we forget about all other seminorms, remember only about p, and consider x as a seminorm space. So this is obviously continuous for trivial reasons. This is just an isometry with respect to this pair of seminorms. Okay, but we already know that from part 2, we know that our result holds for seminorm spaces. So this implies that if we take the injective tensor product of the respective seminorm spaces, x1 with p1, p1, and x2 with p2, then we have a continuous map from this space to the injective tensor product of y1 Q1 and Y2 Q2. This is continuous by part 2. But this is nothing but the injective tensor product of x1 and x2 equipped with the single seminorm phi1 tensor p1 tensor p2. And this is similarly the injective tensor product of y1 and y2 considered as a seminorm space for q1 tensor q2. So now we see that for every seminorm on the tensor product of this form, and seminorms of this form generate the topology of the injective tensor product, we have found a continuous seminorm on this space such that the respective linear operator between the seminorm spaces is continuous. This means precisely that phi1 tensor phi2 is continuous. Okay, so this operator is continuous. And this completes the proof of part 1. And part 3 easily follows from parts 1 and 2 and the universal property of completions. In particular, to show that we have a unique continuous linear map between the complete injective tensor products. Now we simply define it between the uncompleted injective tensor products and then extend by continuity to the completions. Okay. So as a corollary, we see that we have two functors of two variables. The first one is the uncompleted injective tensor product. And the second one is the complete injective tensor product. And it acts to the category of complete locally convex spaces. But again, I'd like to stress that in contrast to the projective tensor product, the injective tensor product is not defined by any reasonable universal property. Okay, now the initial question is, what if we work with normed spaces only? So if you have two normed spaces, x and y, then we can consider them as special cases of seminorm spaces, and so their projective and injective tensor products will be seminorm spaces. But it is natural to ask, maybe they are normed spaces. And the answer is yes, they are normed spaces. And this follows from the next slightly more general result proposition. Suppose that x and y are locally convex spaces, then the following conditions are equivalent. Condition 1, the projective tensor product of x and y is Hausdorff. Condition 2, the injective tensor product of x and y is Hausdorff. And condition 3, both x and y are Hausdorff. To prove this result, let's first observe that 2 clearly implies 1. This is clear because the projective tensor topology is stronger than the injective one, and if this Hausdorff, then this is also Hausdorff. It's a simple exercise to show that 1 implies 3. A good but simple exercise for you. So let's show now that 3 implies 2. Suppose that x and y are Hausdorff, and let's show that the injective tensor product is Hausdorff. Okay, so let's take a non-zero element in the injective tensor product. I'm going to find a continuous linear functional which takes a huge non-zero number. In other words, I'm going to show that continuous linear functionals on this space separate the points. This clearly implies that the space is Hausdorff, and actually this is equivalent to the space being Hausdorff because, well, by the Helmholtz theorem. So use a non-zero element in the algebraic tensor product, so we can represent it in the following form. And represent it as a finite sum from 1 to n, xi, tensor yi, and it follows from the algebraic theory of tensor product that we can choose these elements xi and yi in such a way that x1 to xm are linearly independent, and such that y1 is not zero. Now we apply the Helmholtz theorem, and by using the Helmholtz theorem, we find a continuous linear functional f on x such that f of x1 is not zero, but f of x2, f of x2, f of x3, up to f of xn are zero. Well, more exactly, we define f on the linear span on the vectors x1 to xn in this way. It is continuous because the space is finite dimensional and Hausdorff. And then we extend it to the whole space by using the Helmholtz theorem. And for the same reason, we can find a continuous linear functional g on y such that g of y1 is not zero. Again, we use here the assumption that y is Hausdorff. Let's now look at the tensor product of f and g. By the factoriality of the injective tensor product, we see that this functional is continuous. This is a continuous functional on the injective tensor product. And if we apply this functional to u, what we get is simply f of x1 times g of y1. So this functional kills all summons from 2 to n. And this is non-zero because of by construction, so this is non-zero. And we see that continuous linear functionals on the injective tensor product separate the points. So this implies that the space is Hausdorff. And this completes the proof. So as a corollary, we see that x and y are normal spaces. Then their projective and injective tensor products are normal spaces. And the complete projective tensor product and the complete injective tensor products are R-bound spaces. Okay, let's now look at some canonical isomorphisms related to projective and injective tensor products. I state this as an exercise for you. Exercise 1. Prove the commutativity and the associativity for the projective and injective tensor products and for their conclusions. Property 2 is kind of distributivity. We will have two locally convex spaces x and y. When we form their locally convex direct sum, and then take the tensor product, projective tensor product by another space z, and then get something isomorphic to x tensor z plus y tensor z. And a similar formula holds for the injective tensor product and for the completed versions of the tensor products. Part 3 of the exercise concerns the special case where our spaces are semi-norm spaces. Suppose that x, y, and z are semi-norm spaces. Construct natural isomorphisms of the following form. Natural isometric isomorphisms. Between the space of continuous linear maps from x tensor y to z, and the space of continuous linear maps from x to the space of continuous linear maps from y to z. And if z is a bound space, then we can replace here the projective tensor product by the complete projective tensor product. This holds if z is a bound space. Such isomorphisms are usually called the joint associativity or the exponential lobe. Joint associativity or exponential lobe. Unfortunately, such isomorphisms don't exist in the case of arbitrary locally convex spaces. This is a source of many category-related problems with categories of locally convex spaces. On the other hand, there are some important special cases in which such formulas are true. So this is only one of such special cases, and some other special cases will be discussed a bit later. Okay, so let's now consider some concrete examples of projective and injective tensor products. Examples of topological tensor products. Let's start with a very simple example, which shows that the projective tensor seminorm and the injective tensor seminorm are not the same in the general case. So we know that they are related by the inequality, so the projective tensor seminorm is greater than or equal to the injective tensor seminorm, but it would be good to have an example, to have a concrete example where they are not the same. To construct such example, let's introduce some notation. Suppose that X is a seminorm space. And let's define by x to the power n with the subscript 1 the nth power of x equipped with the following seminorm. The seminorm of an entuple x1 to xn is just the sum of their seminorms. And we also need another space, xn infinity. This is the nth power of x equipped with another seminorm. which is defined to be the maximum of the semi-norms of the elements x1 to xn. So we have the following proposition. There exist isometric isomorphisms between the following spaces. So the first one looks as follows. We take the space Kn and form the projective tensor product with a semi-norm space X, with the semi-norm space X. And what we get is xn1. And if we take the injective tensor product, this is Kn1. We equip Kn with the L1 norm of this form, and we get the following isomorphism. On the other hand, if we equip Kn with the L infinity norm and take the injective tensor product with X, what we get is xn infinity. And explicitly, these isomorphisms take each elementary tensor of the following form, EI tensor X, to the n tuple where we have X in the nth slot and zero elsewhere. Here by EI, I denote the ith element of the usual basis of Kn. So why is it so? Part 1 is actually a simple exercise for you. Basically to get, it's clear that there exists an algebraic isomorphism given by this formula. So this formula gives us an algebraic isomorphism between these spaces. The only point is to show that it is isometric. So to show that it is isometric here, we use the universal property of the tensor product, which implies that this map is a contraction. And the fact that the opposite map is a contraction follows immediately from the triangle inequality. So this map is a contraction, the inverse map is a contraction, and so this map is actually an isometry. To prove the second isomorphism, it is convenient to use a duality argument. So we take our space. We take our space, and as before, we construct an isometry from the space to the dual of the projective tensor product of the duals. But what is the dual of Kn infinity? The dual of Kn infinity is easily seen to be Kn1. This is a finite dimensional case of the usual L1 of the usual duality between L1 and L infinity. And the dual of X is, this is the dual of X. I have the projective tensor product and the dual of this space. By part 1, this tensor product is isometric to X prime and 1, and take the dual of this. But the dual of the nth of X and 1 is easily seen to be X prime and infinity. So this is, as a result, this is X double prime and infinity. On the other hand, we have the algebraic isomorphism between this space and X and infinity. Algebraic isomorphism. Given by this formula. And finally, we observe that there is an isometry from here to here. So this error is in isometry. And this error is also an isometry. Okay. Okay, so all this picture, now the picture shows that this algebraic isomorphism is actually an isometric isomorphism. This is an isometric isomorphism. Now this completes the proof. Okay, now by using this proposition, we can easily construct many examples in which the projective tensor seminorm is strictly bigger than the injective tensor seminorm. Example and an exercise at the same time. Well, let n of k denote the space of square n by n matrices. N by n matrices over k. We have actually an isomorphism between kn, tensor kn, and Mn of k, which takes each elementary tensor ei, ej to the respective matrix unit eij. And now we equip the space with seminorm, actually with a norm. So we put kn1 here, kn infinity here, and the projective tensor product here. So this is a normal space. We can use this isomorphism to make Mn of k into a normal space. But on the other hand, we can consider the injective tensor product of the same spaces. Kn1, Kn infinity, the injective tensor product. So as a result, we get two norms on the same space Mn of k. The exercise is to show that find an explicit formula. Find an explicit formula for the respective two norms, the projective tensor seminorm, projective tensor norm, and the injective tensor norm on the matrices on Mn of k. And by using this formula, show that they are not the same. Of course, if n is at least 2. Of course, if n is 1, then everything is one-dimensional and the seminorm and the norms are the same. But if n is at least 2, then they are not the same. So this is maybe the simplest example, which shows that the projective tensor norm and the injective tensor norm are not the same. Okay, let's now look at something infinite dimensional. Suppose that I is a set, and let's denote by L1 of I, L1 of I, the set, the subspace of the space of all k-valued functions on I. So we think of them as families indexed by I, and satisfying the following condition. When I write such a formula, as usual, I suppose that the elements xi vanish for all but countably many indices I. Actually, if we define the infinite sum to be the limit of a suitable net, namely the net consisting of finite sums, of sums over finite subsets of I, then the fact that xi vanish for all but countably many indices becomes a theorem. Anyway, so L1y is a Banach space. This is a Banach space. This is well known in the case where I is countable, but the case where I is uncountable is similar. So this is a Banach space. And we have the following proposition. I claim that there exists an isometric isomorphism between the complete projective tensor product of L1 of I and L1 of J, where I and J are two sets, and the L1 of the product I cross J, which is uniquely determined by the following formula. EI tensor EJ and goes to EIJ. So I haven't explained what EI means. So let me explain this. So here EI is the element in L1 of I, such that the jth component of this element is the Kronecker delta. Okay, let's prove the result. We will use the universal property of the projective tensor product. Sorry, I forgot to say that this is. I forgot to explicitly denote this projective tensor product by a little pi. So we start with a bilinear map. L1 of I times L1 of J to L1 I times J. This will be denoted by phi. And phi is explicitly given by the following formula. Phi of xy is an element in here whose coordinate number ij is x, I, y, j. So clearly phi is bilinear. Phi is bilinear. And it's a contraction. Its norm is less or equal to 1 for obvious reasons. If we take the sum of all these numbers, what we get is just the norm of x multiplied by the norm of y. So we linearize now. We consider the complete projective tensor product of our spaces. And we get a linear contraction for little phi. Phi is linear. And the norm of phi is less or equal to 1. And by construction, phi takes EI tensor EJ to EIJ. So we want to show that this little phi is an isometric isomorphism. And to prove this, we simply explicitly construct the inverse map. We define psi from L1 of I times J to the projective tensor product of our L1 spaces by the following simple formula. If, say, Uij is a summable family in this L1 space, then we take this family to the following sum over I and J, Uij, EI tensor EJ. Since the family Uij is absolutely summable, and since the norm of EI tensor EJ is 1, we see that this series is absolutely convergent, because the space is complete. So it converges to a well-defined element in our space. Moreover, by the triangle inequality, the norm of this element is less than or equal to the L1 norm of U. So psi is a contraction. Psi is a contraction. And clearly, phi and psi are inverse to each other. To check these identities, we simply look at such elementary tensors and see that we have these formulas. And that's it. So this shows that phi is actually an isometric isomorphism. Phi is an isometric isomorphism. This result, by the way, I'd like to say that if we replace here pi by epsilon, then the result fails. This is a good exercise which will be included in the next exercise sheet. Now, actually, this result can be generalized in several directions. For example, we can do the following. Let's introduce some notation. Suppose that E is a Banach space, and let's denote by L1 of IE to be the set of all elements xi in e to the power I, for which the following sum is finite. The sum of the norms of the elements xi. So this E-valued little L1 space is also easily seen to be a Banach space. So this is the norm on our space. A useful exercise is to construct an isometric isomorphism between the complete projective tensor product of L1 of E, L1 of I, and E, L1 of I and E, and this E-valued L1 space. The argument is more or less the same as in the proof of the previous proposition. In the special case where E is L1 of G, we get what we get is essentially the previous proposition. But the proof was essentially the same. Another useful generalization of our previous proposition. So let's, for convenience, let it be proposition 1. So now we have proposition 2. Suppose we have two measure spaces, x mu and y nu. Measure spaces. Sigma finite for convenience. I claim that there exists an isometric isomorphism. Between the projective tensor product of big L1 of the big L1 spaces, L1 of x mu and L1 of y nu, and the space L1 on the product x cross y. And this isomorphism is uniquely determined by the following rule. It takes every elementary tensor f tensor g to the function h, where h is given by the following formula. This is f of x, g of y. And here is the main idea of proof. Actually a sketch, but well, this will be almost the proof. For convenience, let's consider the special case where x and y are finite vector spaces. So here we assume that mu and nu are finite. First of all, the existence of such a linear map from here to here follows from the universal property of the tensor product. So the existence of phi given by this formula and the inequality that the norm of phi is less than or equal to 1 follows from the universal property of the projective tensor product. always simply linearize a suitable bilinear map. And that's it. So now I want to show that phi is actually an isometric isomorphism. And to prove this, we consider finite measurable partitions of the following form. x1, xn, and y1, 2, yn. Measurable partitions. So we consider two such measurable partitions, and we denote by E the linear span of the characteristic functions of the first partition, xi, and we denote by F the span of the characteristic functions corresponding to the second partition. Now, a simple exercise is to show that if we restrict phi to E, what we get is, this is, sorry, I'd like to slightly change my notation, because let's consider a similar subspace, but in the projective tensor product, which consists of all elementary tensors of the following form. So we consider characteristic functions of the sets x1 to xn, characteristic functions of the sets y1 to ym, and we form the respective elementary tensors. This will be E. This is E. And we denote by F. We denote by F the respective subspace of L1 on X cross Y. So F will be the linear span of all characteristic functions of the products xi cross yg. And now I claim, and this is an exercise for you, that if we restrict phi to E, what we get is an isometric isomorphism between E and F. This is more or less elementary, and the idea is the same as the proof of proposition 1. So since there are finitely many, we have finitely many elements here, and everything reduces to actually to little one spaces, and more exactly to the finite dimensional versions of the little one spaces. So this is an isometric isomorphism. And now if we consider all possible partitions and take the union of the respective spaces E, what we get is a slave vector subspace which is dense in L1. It's dense in the, not in L1, but in the tensor product. And similarly, if we take the same for the spaces F, so each F is actually indexed by a suitable partition. If we take the union over all partitions, what we get is something which is dense in L1 on the product. And essentially this completes the proof. So because as a result we get an isometric isomorphism between dense subspaces, and it uniquely extends to an isometric isomorphism between the whole spaces, this one and this one. And the proof can be easily extended to the case of an arbitrary sigma finite measures. So mu and nu are not necessarily finite. Essentially, the same proof shows that the same result holds for sigma finite measure spaces. Okay. Another useful generalization of proposition 1 deals with the so-called Curtis sequence spaces. So let's introduce Curtis spaces. Suppose that R is a set, and suppose that P is a set of non-negative real-valued functions on R. So if little p is an element in P, we think of this function as a family of negative numbers indexed by I. So by the following definition, the Curtis space, before we define Curtis space, we make some restrictions on P. So we say that P is a Curtis set. Is a Curtis set. If it satisfies the following conditions, first of all, it is separating in the sense that for every I, there is a function P in P such that the ith coordinate Pi is strictly positive. And second, P is directed for any two elements P and Q in big P. We can find a constant and another element R in P such that the maximum of Pi and Qi is less than or equal to CRI for every I. If now P is a Curtis set on I, then we define the Curtis space. The Curtis space lambda 1 of IP to be the following vector space lambda 1 of IP. It consists of those elements xi in k to the power I, so they are simply functions from I to k, or families of elements indexed by I, such that for every sequence P in big P, the following number is finite. So we simply take the pointwise product of xi and pi and calculate the L1 norm, L1 of I. So this has to be finite for every P. And similarly, if we replace here L1 by L, well, not LP because P is already in use, let's denote it by nu. So similarly, we can define lambda nu of IP for every nu between 1 and infinity, including infinity. It's a simple exercise to show that lambda nu of IP is a vector subspace of the space of all k-valued functions on I, and it is a complete locally convex space for the topology generated by the family of all such seminorms. So the seminorms are indexed by elements of the respective Curtis set. The completeness is proved in exactly the same way as the completeness of little L nu spaces. Let's look at some concrete examples. Example 1. So for simplicity, let I be the set of natural numbers. The respective Curtis set will be countable, P1, P2, and so on. Where the nth sequence Pm looks as follows. Then I claim that the respective Curtis space lambda nu of np is nothing but the set of all sequences equipped with the standard product topology. This is used as a simple exercise. Note that it doesn't depend on nu. So the seminorms are different, but the topology doesn't depend on the choice of nu. Example 2. Example 2. If P, again, suppose for simplicity that I is the set of natural numbers, and P consists of a single sequence, all of whose elements are 1. Then, of course, the respective Curtis space is nothing but the little L nu space. L nu of 1. Example 3. Let I, again, suppose that I is a set of natural numbers. P is countable. P1. P1, P2, and so on. And the sequence Pm looks as follows. Its kth coordinate is k to the power n. Then the respective Curtis space lambda infinity of P is nothing but the space little s of rapidly decreasing sequences that we have already met at the first lecture, or the second lecture. This is the standard discrete analog of the Schwarz space. Moreover, I claim that we can take actually L nu of np for an arbitrary nu, but we still get the same space little s. This is useful exercise, which was implicitly hidden in one of the previous exercise sheets. Example 4. Example 4. Let I be the set of all non-negative integers. P, let's go to set P will be countable. P1, P2. And the sequence Pm is given by the following formula. Its kth coordinate is m to the power k. So here we have k to the power m, and here we have m to the power k. So what the difference? Well, I claim, this is also a simple exercise, that the respective Curtis space lambda u of I p is isomorphic to the space of holomorphic functions on the complex plane for every nu. This is also an exercise. And the isomorphism is quite explicit. It takes every holomorphic function on the complex plane to the sequence of its Taylor coefficients at 0. Example 5 is a useful generalization of of example 3. So suppose I is the set of all n tuples of non-negative integers. The Kyoto set P is countable, P1, P2, and so on. And the M sequence looks as follows. Its kth coordinate, where k is now an tuple of non-negative integers, is the absolute value of k plus 1 to the power n. Here I'm using the standard multi-index notation. So if k is the n tuple k1 to kn, then we define the absolute value of k to be the sum k1 plus kn. So I claim that the respective Kyoto space, lambda nu, is isomorphic to the space s little s of z to the power n of rapidly decreasing sequences indexed by n tuples of non-negative of course we can consider non-negative integers, but it will be more convenient for us to take arbitrary n tuples of integers. Also negative numbers are allowed here. And why do we need all integers? Well, because the Fourier transform gives us a topological isomorphism between this space and the space of smooth functions on the n-dimensional torus. So we see that the space of smooth function on the n-dimensional torus is also a special case of Kyoto space. And this is true for every nu.
А там после нуля, наверное, не нужно, да?
Thank you. Thanks. Example 6. Example 6 is a generalization of example 4. We take an tuple of positive real numbers Also, some of them may be equal to infinity. This is also possible. And we denote by dr the respective polydisk in the space Cn, which consists of these points of Cn, Z1 to Zn, such that the absolute value of Zi is less than Ri for every I. This is the open polydisk of polyradius R. Now we construct the following Kyoto set. So the index set will be the set of all n tuples of non-negative integers, and the Kyoto set P consists of all sequences of the following form: R1 to the power K1, R to the power K2, and Rn to the power Kn. So we take the product. Here, K runs over over set of all multi-indices n tuples of non-negative integers, and we will Ri are strictly between 0 and big Ri. So for every K, we consider the following sequence. And the Kyoto set consists of all such sequences. Then I claim that the respective Kyoto space, lambda nu of P, is isomorphic to the space of holomorphic functions on the polydisk Dnr for every nu. This is also an exercise, but the isomorphism is actually the same as in example 4. It takes every holomorphic function on the polydisk to the family of its Taylor coefficients at 0. Well, our last example 7. Example 7 is the space of germs of holomorphic functions at a point on the complex plane. So let's denote the space by O sub 0, the space of germs of holomorphic functions at the origin on the complex plane. So we know that this is a locally complex space for the canonical inductive limit topology. So the respective Curtis set will be just this set of non-negative integers. And this is the index set, and the Curtis set P consists of all those sequences Pn of positive numbers such that Pn behaves as follows. Pn goes to 0 faster than epsilon to the power n for every positive epsilon. I claim, this is an exercise, which is a bit harder than the previous ones, that the respective Curtis space lambda nu of P is topologically isomorphic to the space of germs of holomorphic functions at 0 for every u. The isomorphism is the same. It takes every holomorphic germ to its sequence of Taylor coefficients at 0. As a byproduct, we see that this space of germs of holomorphic functions is complete. As a corollary, this space is complete. Because the respective Curtis space is complete. Okay, so that's all for today. We had no time to describe the projective tensor product of Curtis spaces, but we will see at the next lecture that the projective tensor product of two Curtis spaces of the form lambda 1 is again a Curtis space of type lambda 1. And as a corollary of this result, we will explicitly characterize complete projective tensor products of spaces of smooth functions on the torus and of spaces of smooth functions on open polydisks. And after that, we look at the injective tensor product and discuss some concrete situations in which the injective tensor product is more relevant than the projective tensor product.